still have to submit this? Can I bring it in like before class ends?
Yeah. Everybody got his stuff up here? For you folks doing 46L early tomorrow afternoon, because you are also going to do the 46 lecture exam tomorrow night, Carleton, 7 p.m.
Can I ask you a question? I turned mine in.
That's all. Look, if you turn this form in and leave 214, don't worry, I'll get it. No big deal. Back to this. For you folks doing 46L early tomorrow afternoon, because you're also doing the 46 exam tomorrow evening, we will ask that you gather at 4:50 p.m. tomorrow, just for the 46L early birds in Lee 142. Give me a show of hands how many of you here are involved in that. Not too many. Okay. Now, back to chapter 23. We are assembling a collection of factors, each of which may well relate to explanation, providing a basis for rationalizing Bronsted-Lowry acid strength. What have we looked at so far? Charge to size ratio. That allowed us to determine this acid strength relationship. Negative charge density stabilization due to atomic electronegativity. That allowed us to rationalize this relative acid strength trend. Induction. We looked at these three acids yesterday, recognized they are structurally identical. Each on H plus loss loses a negative charge. Creates a negative charge on the oxygen on oxygen atom. So if the negative charge were to just stay on oxygen, these acids would be the same strength. But these acids are considerably different in strength. This is much stronger than this, which is much stronger than that. So we recognized that for these two acids in particular, the terminal fluorine atoms for the first acid and chlorine atoms for the second acid exert stabilization on the site of negative charge development, on the negative charge itself, by extending electronegativity effect through the covalent bond skeleton of the species. That's called induction. These atoms, due to their high electronegativity, induce that negative charge to be drawn toward themselves, and in so doing smeared across the covalent bond skeleton. The greater the degree to which the negative charge density is smeared, the more dilute it is, the weaker the base, the stronger the corresponding conjugate acid. Then we looked at how induction relates to length of covalent bond skeleton. Found out that once you get the highly electronegative atoms far removed from the site of development of negative charge, their ability to stabilize negative charge density by induction is lost, practically speaking. Here, induction still significant, or is significant. Here, where we've added a carbon atom to extend the length of the carbon skeleton of the species by one atom, very little induction stabilization of the developed negative charge density by loss of this H as H plus. Orbital electronegativity. Here, developed negative charges on an sp carbon. Here, sp2 carbon. Here, sp3 carbon. The greater the s character of a hybrid orbital, the greater is its orbital electronegativity, and the more effectively that hybrid orbital stabilizes negative charge density, making this the strongest of these three acids. Now, these are all very feeble, weak acids. Nevertheless, they do exhibit measurable acid strengths. Not in water solvent. You got to go to a different solvent. You'll talk about solvent systems in which such effects can be observed when you're in organic next term. Resonance. We have already recognized that resonance is a very important valence electron property, but which cannot be adequately represented by writing Lewis structures. Because for these two species, to revisit these cases, there are no NO single bonds, no NO double bonds. NO bond lengths and strengths identical, bond order 1.5. NO bond lengths and strengths identical, bond order 4/3. But unfortunately, it's impossible to draw pictures of a part of a bond. So you just have to recognize such by realizing I could just as soon write this Lewis structure with the double bond here rather than here, or the double bond pictured here rather than here or here. Those are the three resonance forms for nitrate ion. For this I have two resonance forms, neither of which is representing the true valence electron structure for the species. Okay? Now between these two, which I think one aspect of resonance we didn't touch on yesterday, is which of these will stabilize negative charge density more effectively by by resonance, pardon me. Which of these will stabilize negative charge density more effectively by resonance? Which shows the greater resonance effects? And the answer is that species for which you can write more acceptable resonance forms. No more, no less. 3 resonance forms versus 2. So this is better. Now you can also come to that realization if the species in question have the same total degree of charge, like these, they're each -1. By recognizing the true formal charge on each peripheral oxygen. We did this yesterday. What is the true formal charge on each peripheral oxygen for this thing? Because if you analyze this as it stands, as it's illustrated, formal charge, this is -1, this is 0. But these oxygens are electronically equivalent. That's the part of the puzzle you can't represent by drawing a picture. So their true formal charges, -0.5, -0.5. Here, the true formal charge is -1/3. Well, -1/3 is smaller formal charge than -0.5, isn't it? Another way to look at it. How about this? What's the total formal charge of this species? Have you recognized by now that when you see a so-called singly bonded oxygen, it has a formal charge of -1, and a doubly bonded oxygen has a formal charge of 0? What is this thing? Carbonate ion. -2. How many resonance forms? 3. So this too effectively stabilizes negative charge density by resonance. Okay? But carbonate ion is a whole lot stronger base than nitrate ion. Carbonate ion is a whole lot stronger base than nitrite ion. Why is that? Don't overlook the obvious.
-2 charge versus -1.
The total minus charge of that is twice the total minus charge of either of those. And now 7. So-called principle of maximum overlap. Did you talk at all in 2045 about orbital overlap interactions regarding when they are effective and when they are not so effective? For example, if you want to make a stable pi bond with p orbitals, how do we want the p orbital lobes oriented in space with respect to each other? Parallel. Okay? If one p orbital has its lobes in the up and down direction, and the other p orbital, which is going to overlap with this thing to make a pi bond, has its p orbital lobes not quite parallel, you can still get a pi bond, but it won't be as strong as this pi bond. Now then, in the main, what this PMO relates to try to make it as simple and straightforward as possible, is to realize that multiple bonding is generally stronger between small right side period 2 atoms, like carbon with carbon, or carbon with nitrogen, nitrogen with oxygen, carbon with oxygen, than with period 3 atoms or period 4 atoms. And generally stronger pi bond or multiple bond formation between period 2 atoms exclusively than if I have pi bond formation with period 2 and period 3 atoms, or period 2, period 4 atoms, or period 3, period 4 atoms. Well, regarding size, why should we expect multiple bonding for the smaller atoms, carbon, oxygen, nitrogen, to be stronger than multiple bonding for larger atoms? Multiple bonding is a consequence of pi bonding.
Because of
What?
electron density.
Well, you're talking about electron density. About electron density, you're talking about bonding electron density?
No, there's the density of the negative charge is greater on smaller atoms. And
Well, we're not talking about negative charge now. What we're talking about is how effectively the pi bonding electron density will be stabilized when I have bond formation interaction with the smaller atoms versus the larger atoms.
Would the effective be more stabilizing because there's less shielding in smaller atoms?
Well, you're getting there. In the main, it's a size effect. The smaller atoms will have the bonding electrons closer to the mutual nuclei of the bonding atoms. The closer to the nucleus, the more stable the electron density. So, here, imagine this is simulating formation of a pi bond by p orbital overlap, with the p orbital lobes being mutually parallel for period 2 atoms. Where are the nuclei of the atoms? Here and here. And here's the bonding electron density. Simultaneously occupying this region in space that's above and below the internuclear axis connecting the nuclei. I mean the internuclear axis, okay? But here, this pi bonding electron density is pretty close to these nuclei. Well, that factor falls off when I get pi bond formation with larger atoms. Now pi bonding electron density is further from the nuclei. And if I have pi bond formation with a larger atom and a smaller atom, same problem. Plus, although this picture, you're just going to have to take it for granted, you don't get as effective orbital overlap. Because, from a theoretical standpoint, that's what orbitals are. The degree or percent of overlap versus unoverlapped portion of the orbitals is directly proportional to bond strength. So here's the overlap regions. The empty parts are the unoverlap regions. Here's the overlap regions. The empty parts, the unoverlap regions. Here, overlap regions. The empty parts, the unoverlap regions. At a glance, I think you'll recognize here the percent overlap region of the whole region is greater than it is here or here. Stronger bond. Now let's take a look at an example where we can see this PMO from a more practical standpoint. Nitric acid, chloric acid. All right? We want to compare the Bronsted acidities of these two acids. What do we do first? What do we do first? How are we playing this game?
Lewis structure.
Lewis structure for what? Lewis structure for conjugate base. Okay? And we've already got the Lewis structure for nitrate ion on the board, but I'll re-sketch it. Chlorate ion showing ClO single bonds only. Well, let's see for this Lewis picture if we can reduce the degree of indicated formal charge smear by imagining resonance to be a property of this anion. So, we take non-bonding electron density from the atoms bearing the negative formal charge, like this, and advance such to bonding status. Advance it toward the atom which bears the positive formal charge. Right? Minus travels toward plus. Nothing fancy about that. That's just Coulomb's law applied to analyzing Lewis structure. Now, this oxygen will become 0. Now the central chlorine atom will be +1. Well, let's play the game again. Now this oxygen 0, this oxygen 0, this chlorine 0. And now the only atom bearing formal charge, based on these resonance considerations, is this imagined singly bonded oxygen atom. But if this resonance picture is true, is there a singly bonded oxygen atom? Are there two doubly bonded? No. All the bond lengths and strengths will be the same. And that is true for this ion. All the bond lengths and strengths are the same. But what we are really wishing to ask is, how valid is this Lewis structure? Valid is resonance important for chlorate ion? Is that an important property of chlorate ion? Well, without considering resonance, how should I expect the acidities of these two to compare? Well, let's look at the factors we've already paid attention to. Each have 3 peripheral oxygen atoms. And in what fashion do peripheral oxygen atoms, these peripheral oxygen atoms, in what fashion do they contribute to negative charge density stabilization? Which of these factors? Which? I'm listening. Are oxygen atoms number 2 in the electronegativity rank? So will these oxygens stabilize negative charge density effectively by which one? Which one? Which one? Each of these species bears a total minus charge of only -1. Okay? We're asking for these species In what fashion do the oxygen atoms contribute to stabilizing the negative charge density of -1? How did the fluorine atoms and the chlorine atoms contribute to stabilizing negative charge density for the anions of these acids? By this, didn't they? Do not oxygen atoms exert a significant induction effect on negative charge density stabilization? Second only to fluorine, because oxygen atoms are the second most electronegative atoms, right? Okay. So we've got equal degrees, or presumed equal degrees, of negative charge density stabilization by induction, at least approximately equal. Because in each case, wherever you imagine this minus charge to be, the oxygen atoms are of the same proximity to that site of negative charge. Because you got one central atom and oxygen peripheral atom, nothing else. How do the chlorine, nitrogen, and central atoms compare from an electronegativity standpoint? Do they also contribute to negative charge density stabilization by induction? Nitrogen and chlorine? Are they atoms of appreciable electronegativity? Yeah, sure. And if resonance is a significant property for chloride ion, I'm spreading this negative charge over a larger surface because the chlorine atom is bigger than the nitrogen atom, right? So far, on the basis of what we said so far, how do you think the base strengths of these two anions will compare? One much stronger than the other, or about the same? About the same? Yeah. Each has a central atom of appreciable electronegativity. The electronegativities of nitrogen and chlorine are about the same. Each have 3 peripheral oxygen atoms to stabilize negative charge density by induction. And if chloride ion shows resonance as an appreciable property, we could well expect chloride ion to be a weaker base than nitrate ion. Certainly not less weak. So now we run to the laboratory. And we make water solutions of each of these acids at the same molarity. We already know about this stuff. It's a strong Bronsted acid. Ka is very large. And find out that Ka this is a whole lot bigger than Ka this. This is a much stronger acid than this. So we got to go back to our explanation drawing board. Something seems out of whack. So look at this, or recall this PMO consideration. If we're going to have an effective pi system, we need to have the lobes of the orbitals, which overlap with each other to make the pi system, mutually what? Parallel, right? Okay. Now then, you see this model? For which of these anions do you think this is a model, and why? Nitrate ion. Why? How's this N atom hybridized?
sp2.
How's this chlorine atom hybridized? sp3, right? What kind of general geometry do you associate with sp3 hybridization? Huh? Tetrahedral if you got 4 peripheral atoms, but here you only got 3. So what's the shape of this thing? The shape of this thing. What is the shape of this? Trigonal pyramid. Has the same shape, for example, as an ammonia molecule. What's the shape of this thing? What is it? Trigonal planar. And with trigonal planar geometry, an sp2 hybridization for every component atom. Because you remember what we said? If you've got an atom which has got non-bonding electron density, covalently bonded to an atom which is sp2, this is an sp2 central atom, then these atoms are also sp2, right? And that's what the model shows. Each of our peripheral oxygen atoms, including the central weak lobe, I'll turn it over. Okay. Each of the peripheral oxygen atoms, including the central nitrogen atom, all have a p orbital available for overlap with each other to make a pi system. And what is the geometric orientation of these p orbital lobes with respect to each other? Mutually parallel, right? Because this thing is planar. But how about this other character? Well, let's take a look at a model of the other character. And we'll take one of these loops. To simulate one lobe of an orbital which the chlorine atom will have available for pi bond formation. Okay? Now, I don't care how you orient the lobes of the peripheral atoms for chlorate ion, you cannot have mutual parallel orientation of the orbital lobes which would form the pi system for this species, because it's trigonal pyramidal. So I cannot have effective orbital overlap. Principle of maximum overlap also says for nitrate ion I got atoms which are right next door to each other in period number 2, aren't they? They're small atoms of the same size, orbital overlap effective. That's the PMO game. Here, the central atom and the peripheral atoms are from different periods. Not nearly as effective orbital overlap. Plus, this thing isn't planar. Furthermore, we've stated the rule. If a peripheral atom or an atom that has non-bonding electron density is bound to an sp2 atom, then that atom is also sp2. Okay so far? Well, these atoms have non-bonding electron density. But is this atom sp2? No, this is sp3. So based on this consideration, we have no cause to really believe these atoms are sp2 in character. We don't really have good reason to believe there's any appreciable degree of resonance or multiple bond formation at the chlorine-oxygen bond sites for the chlorate ion. What would we do to find out? Only one way to find out for sure. Let's go to the lab, and in this case, measure bond length strength properties for each ion. And we find out the NO bonds are a heck of a lot stronger than the CLO bonds. Now, that part of the puzzle you wouldn't know about. You don't know about going to the lab, but you know about the arguments. And now we have recognized, this is very important, particularly in organic class. If resonance is to be an appreciable property of a species, an appreciable property of the species, whatever the species might be, all the atoms which are part of the imagined resonance system must bear what kind of hybridization? sp2, so that they all have a p orbital available for multiple bond formation. Remember, we're talking about organic molecules where the principal skeletal atom is carbon. That's period 2 atom. Okay? And in addition to sp2 hybridization, what must be the overall geometry of the species? Planar, you betcha. Now, you'll see some organic molecules for which all the atoms imagined to be part of a resonance system are sp2 hybridized. But resonance is still not going to be an important property of this thing because of steric hindrance, which does not allow resonance to be appreciable. Did you recognize that in wrestling with special quiz number 3? Huh? Any question I asked you about the substituted xylenes? Because one shows appreciable resonance, the other one does not. And that's what's going on here. Now, with that, we now have reasons to realize why Ka this a good deal bigger than Ka this. We proceed. Other factors. We've added PMO as number 7. Now number 8. Solvation. First, take note. The word I wrote on the board is solvation. It is not salvation. I do not know how to provide you with salvation, but I can discuss with you solvation. What is solvation? At this stage of the game, if I ask you to give me a simple definition of solvation, what would you say? You think this relates to solvent? Solvation? It relates to interaction of solute species with solvent molecules, no more, no less. Solvation. Simple example. I pick on this example because I've seen data reported for Ka measurements of acetic acid in ethanol as solvent. Ethanol, you may recognize, is the active ingredient in potable spirits. CH3, CH2, and an OH group covalently bonded to the CH2 carbon. Okay? We know that Ka acetic in water, 1.8 times 10 to minus 5. How do you think Ka observed for acetic acid and ethanol will compare? You think it'd be the same? Higher or lower? The answer lies in solvation. Now tell me, when acetic acid reacts with water, what are the products? Products are hydronium ion and acetate ion. Okay? When acetic acid reacts with ethanol, you get, I guess, what we can call ethanolium ion or something like that. Because what are you going to protonate in ethanol? We played this game before. You're going to protonate this oxygen. If for no other reason, that's the only side of non-bonding electron density that the ethanol molecule has. So when you make protonated ethanol, you get this thing. Okay? And of course, acetate ion. So the answer to this question lies in the relative stabilities of hydronium ion AQ and acetate ion AQ, because these are the products of acetate ion reacting with water, versus the stabilities of this in ethanol solvent and this in ethanol solvent. In which solvent system will these ion products, they're ions, right? We made ions. Started with molecules, made ions. In which solvent system will these ions as products be more stable? Water or ethanol? Water, why? Well, I think the simplest way to ask the question is, which material is far more electric in nature, water or ethanol? Water, you betcha. So, water stabilizes the presence of ions by solvation far more effectively than ethanol molecules. Because the water molecules, like ions, the water molecules are more electric in nature. That's it. You know, so if you can sum up polarity, hydrogen bonding effects, then you can answer questions like this. Now, I have no intention to ask any questions about this solvation consideration, because we have not done anything with any solvent except water. But still, it's important, and you'll talk further about this, I'm sure, in organic class. So just to make the list complete, we'll leave that up there as factor number 8. And we go to 9. Well, if you look in the notes at this stage of the game, you'll see some discussion about oxoacids, but in truth, we've already discussed oxoacids. So what I want to do now is to be sure you recognize what the term oxoacid means. Because that, in the notes as they stand, is an out-of-place topic. Oxoacids simply refer to acids which, after H plus loss, provide negative charge density stabilization because of oxygen atom induction. That's it. And we've looked at that. Nitrate ion, chlorate ion, any of these. That's all it is. So when do you know an acid is an oxoacid? You know because its anion species will have one or more oxygen atoms on the periphery. That's all. Which is easily recognized by writing a Lewis structure. So we'll write that down. Oxoacid. I'll define it this way. Any Bl acid which on H plus loss produces a CB conjugate base which has at least one singly bonded, well, never mind the singly bonded, at least one peripheral O atom. To provide stabilization of negative charge density by induction. Enough said. Now, number 9, last factor. Central atom ox state. Oxidation state. Oxidation number. Okay? Let me put a couple acids on the board where consideration number 9 will apply. For these two cases, which relate to the chloric acid, HOClO2 stuff we talked about a moment ago, okay? Anion this. Anion this. Now, we've recognized this will stabilize its negative charge density more effectively because of 2 oxo-oxygens to stabilize by induction versus 1. Okay? What's the oxidation state of this chlorine atom? You get this? This is -2 and the whole thing is minus. Well, what's the oxidation state of this chlorine atom? +3. So tell me, based on central atom oxidation state, where will I get the greater negative charge density stabilization? Plus attracts minus, doesn't it? This is the more positive oxidation state central atom. So this in turn will draw negative charge density toward itself more effectively than that, because this is a higher positive oxidation state. That's all this means. This central atom positive oxidation state. So let's look at these two. Imagine now that you're asked to analyze these two acids. compare the relative Bronsted-Lowry acidities as a consequence of your analysis. What will you do? What are you going to do first? Draw the Lewis structure for what? Let's do it. You think you might need to pay attention to this consideration for the final? By the way, the final's done. I finished it last night. So later this afternoon, if I can find a moment to do so, I'll post some information about the final. You know what like I told you I would? Okay. But I got a staff meeting 5 o'clock and who knows what all. Because now I get the impression the registrar is raising hell about my request to have this room for Saturday so I can accommodate you folks. Because they have their rules. They don't pay attention to anything called common sense. I know what they're going to tell me. You are absolutely required to have all the finals finished by Friday. Well, you can figure out how to make this Friday. It'll be 82 hours long. I'll do it. I'll figure out something. Don't worry. We'll stick with our plan. I knew I should have never called them. I should have just said, let's come in here, do it. It would have been no problem. As long as you don't let the... Never mind. Stuff goes on all the time around here. In any case, have you written the Lewis structures for the conjugate bases of these things? We've already done this one, right there. sp2, resonance stabilization of negative charge density. 3 atoms of appreciable electronegativity to stabilize negative charge density by induction. So what do we got? Each anion is -1. Okay. This anion is composed of more atoms than this anion. This anion stabilizes negative charge density because of 2 oxo-oxygens, as does this. This is not an oxo-oxygen. This oxygen is also bound to a hydrogen atom. These are oxo-oxygens, this is not. Okay. And to some extent, this will show resonance stabilization of negative charge, but not as effectively as this, because this is an sp3 sulfur, whereas this is an sp2 nitrogen. And we've, just a moment ago, taken a look at what happens when you don't have sp2 hybridization for all the component atoms of a possible resonance system. But it is true, because you can't ever dispute the facts if the facts have been correctly determined by experiment, that this acid is somewhat stronger than this acid. This acid is somewhat stronger than this acid. So of all the factors we've considered, as I see it, the only one which really supports the conclusion that this acid is stronger than this acid is this last argument we've offered. What's the oxidation state of this nitrogen? What's the oxidation state of the sulfur? Not formal charge. You know how to play the game. Whichever Lewis structure you look at, you're going to parcel like this, aren't you? Okay. S by itself, 6 valence electrons, so plus 4. Here, plus 3. Right? 5 minus 2. The only argument I can find to support the fact that this is a somewhat stronger acid and there's not a big difference, but this has a bigger Ka than this. I got the data here, I believe. Let's see. Yeah. This is 7.2 times 10 to the minus 4. And this is 1.3 times 10 to the minus 2. Good deal stronger. So, maybe there's some other factors which as yet we've simply not recognized. Maybe you want to do a PhD in chemistry, trying to find out what's going on here in addition to what we've considered so far. Have at it. Okay? Now, one more issue. And that is question 2332 and question 2333. (2332) we've already talked about. We recognized that if I wish to rationalize the fact that HBr is a stronger acid than HCl, I must rely on the charge to size to assess charge density, negative charge density consideration, rather than electronegativity. Because chlorine is more electronegative than bromine. So with chlorine being more electronegative than bromine, I will argue that on that basis the chloride ion is a weaker, more stable base than the bromide ion. But this is the stronger acid, so its conjugate base, bromide ion, is weaker than the conjugate base of this chloride ion. And the electronegativity consideration does not support that conclusion. So I go to charge to size, because the bromide ion is a lot bigger than the chloride ion. And I rely on this because it fits the facts, no more, no less. Now I look at these two. Did you recognize from our acid-base table that the strongest acid listed in our acid-base table is this stuff? Perchloric acid. It's the strongest known mineral acid. Mineral acid means it's derivable from minerals that you find in Earth's crust. No more, no less. Okay? Perchloric acid, that's one dandy strong acid. Got a Ka value that's something like 10 to the 60. Nope. And as we have been doing, to pursue the matter of the difference in acidities between these two, we look at the Lewis structures to start with for the conjugate bases. So we have them constructed. We see an extreme degree of similarity. Central atoms are each how hybridized? sp3. So the geometry of each of these is tetrahedral. They each stabilize negative charge density by induction with 4 oxo-oxygens. They each stabilize negative charge density by central atom induction. Not as great as the oxygen atoms, but chlorine has an appreciable electronegativity of 3.0, 3.1 some tables. Bromine 2.8. 2.9 in some tables. Which of these is the larger anion? This one, isn't it? Because the bromine atom is bigger than the chlorine atom. Okay? So if we conclude that this is the weaker, more stable base than this, on the basis of this comparison, okay, then we conclude that this acid is stronger than this acid. These are both very strong acids. But that one's stronger. So this charge to size argument must not be what gets at the heart of the matter. So I ask this question. Chloride ion, bromide ion. Big difference in size. These two ions. Do you expect to observe a big difference in size between these two ions?
Yes.
Think so?
Yes.
If I have a nickel and a penny, the nickel's 5 times more valuable than the penny. Now if I had 5 pennies to the penny and 5 pennies to the nickel, what does the ratio in value fall off to? Is it 5 to 1 anymore? Nowhere near 5 to 1 anymore, is it? Okay. So let's play the game, same game with size. Okay. If I have a basketball and a softball, at a glance we see the basketball is a whole lot bigger. All right. Now let's start gluing baseballs to the surface of each object. If I glue 8 baseballs to the surface of each object, will I still have the same difference in size? Okay. If I don't care about baseballs which can immediately touch the surface of the softball, basketball, and I keep on gluing extra layers of baseballs, do you think if I have 1,000,000 baseballs in one box and 1,000,000 baseballs in another box, okay? 2 separate boxes, each containing 1,000,000 baseballs. In one box I stuff a basketball in there, and the other box I stuff a softball in there. You think I'm going to see much difference in size between these 2 boxes now? No. So when you add on all these additional peripheral atoms, the size difference falls off considerably. So bear in mind, we recognize that as you go down a family atoms, down a family, okay, acid strengths are getting stronger for the hydrogen derivatives of the elements, right? We did that. HF weaker than HCl, blah, blah, blah. HI the strongest of those, okay? But when you start putting on all these peripheral oxygen atoms, and create acids, then the game is different. So, of these considerations which we have made, what considerations could we use to keep with the fact that this is a weaker, more stable base than this? From a numbers standpoint, I erased it. I'll put it back. How about this one? Do you think I'll have stronger bonds here than I will there? Because these atoms are closer in size. These atoms are different, separated from by 2 periods. These just by 1 period. Okay? So here I'll have better orbital overlap than I have here. So whatever degree of resonance I'm going to observe for either of these species is certainly going to be expectedly stronger here because of greater PMO. And why do I rely on such an argument? Because it supports the facts. That's why. That's the only way we can play the game. Pay attention to the facts and see what arguments you can come up with that fit the facts. Now, we have in sum concluded the conversations that we have wished to share with you regarding this wonderful 2046 gathering. So what my intentions are for tomorrow will be to be here at our tee-off time for class, and for the duration of the scheduled class time, the 75 minutes, if any of you wish to appear and ask questions in regard to the final, I'll do what I can to entertain you. So we'll use it as a review session, but the review session has to be inspired by you folks. In other words, you have to ask questions. And if you don't do anything more than take a past final exam and say question 24 on the exam from spring 14, that's good enough. Because I'm going to bring with me final exams for 2046 for the last 3 or 4 times I've taught this gathering. Okay? And keep in mind that if you go back far enough in the collection of finals for 2046 that are available to you, you will come on exams which contain questions from chapter 24. That will, of course, not be there because we didn't get there. Okay? 3 or 4 more days, we'd go through the whole 9 yards. But we don't have the 3 or 4 more days. I guess that's another reason because I can't stretch Friday into 82 hours or whatever the heck it is. So with that having been said, we'll see you tomorrow, and later this afternoon I'll try to post some information regarding the nature of the final.